All right. So tonight's LeetCode, I think, is a good one. At least I like it. All right. So let me pull it up from the announcements. Sure, we're working on the thing. So we're doing cookies, assigning cookies. Okay. So again, guys in the room, you haven't looked at this yet, right? Okay, cool. So just aside, I am going to give you guys some time to work. We're going to talk through approach, but I'm going to give you time to try to hack it out because we do have time tonight. Okay, so signing cookies. All right, so let me just do a quick run through. Assume you are an awesome parent and want to give your children some cookies, but you should give each child at most one cookie. Each child has a greed factor, G of I, which is the minimum size of cookie that the child will be content with. And each cookie, cookie J, has a size, so S of J. If S of J is greater than or equal to G of I, right? So if the size of the cookie is greater than or equal to the greed of the child, we can assign that cookie, cookie J, to child I. And that child will be content, right? Intuitive. I mean, it's a more formal like way of saying it, but if kid has a minimum size of cookie they'll be happy with. If the cookie is greater than or equal to that, kid's happy. Your goal is to maximize the number of your content children and output the maximum number. Okay, so here's a couple examples. If the input is, we have a list 1, 2, and 3, and the cookies are 1 and 1, your output's going to be 1, right? So you have 3 children and 2 cookies. However, because, right, the greed factor of the 3 children are 1, 2, and 3. Even though you have 2 cookies, since only one child will be satisfied with 1, you can only assign 1, right? So that's that first example here, 1 and 2. So greed is 1 and 2. S is 1, 2, and 3. So 2 children, 3 cookies. So greed factor of the children is 1 and 2. So you have 3 cookies. Their sizes are big enough to gratify all the children. So you can now assign 2 cookies to them. All right. So any questions on that? So again, so you're given 2 lists. So again, with this, you're given 2 lists. You're given a list of greed. So a bunch of children with associated greeds. You're given a list of cookies with their associated size. And you want to try to come up with an algorithm that maximizes the total number of satisfied children. Okay, let's see. So constraints. So we have overall size constraints. And then, okay, yep, size and things. Sure. Okay, yep, size and constraint boundaries. I don't think anything that'll impact us. All right, so let me pause there. Let's talk. What are we guys thinking for this?
I know you said being greedy.
Yeah.
But I was just wondering how can you use the greedy algorithm with like, I guess, like a nested array? Well, it's not necessarily a nested array, but with 2 different arrays.
Mm-hmm.
No, that's the one thing you should not do.
Yep. So okay, so good question. So the question, sorry for those watching the recording. So there's a question sort of how do we do greedy when we're looking at 2 arrays, right? 2 sort of nested work because we have greed and we have size. And so greedy, so greedy is essentially sort of traversing arguably both of these lists once. And oftentimes the trick is when and how to traverse them. So you can be just one list, right? That you go through, depending on the use case, it can be one, or it can be both of these. You can just sort of decide when and how to do it. You may remember we sort of did actually a version of 2 where we had, do you remember we did the train platform problem in class where we had arrivals and departures? And so we had, right, and we had them sorted and then we just kind of traversed both of them and did that pointer. So you basically kind of ran a pointer there. So, so as long as you sort of traverse both of those lists once, you're still going to kind of get that desired greedy runtime for this. So, okay, so let's take a quick recap. I don't know if you guys had a chance to look at the material on greedy. Okay, so just a reminder, and also for those of you who are looking in this Slack. So I put in the thing here. So I put two sort of greedy lecture material stuff. Okay, so basic greedy and some more greedy stuff from my UCLA algorithms course. Okay, but here's a quick recap on greedy, because again, right, there's a little bit of an intuition we need to develop on greedy. So, okay, basics of greedy. So generally speaking, when you get an algorithm like this, there is an exhaustive way of doing that. And already we can sort of think what an exhaustive way of doing this, right? You try to just allocate every cookie to every kid, and eventually you'll find like just try every permutation of cookies to kids, and for each of them store how many kids get cookies, and then return the max, right? We could do that. That's not great. It's going to be, it's it's O of S times G. So that's not great. We don't really like that. But we could do that, right? That's my sort of exhaustive thing. Greedy says, let's figure out sort of a basic kind of organizing principle for how decisions should be made, right? So there should be an overall organizing principle that would allow me to make a very simple, allow me to sort of traverse through my list, and for each element in my list, make a simple calculation and a simple decision. And again, it's a local decision. You're not making global things. You're not looking at every possible permutation. You're just looking at one specific item in your data, and you're looking through, and you're making one basic calculation, and you're making a decision, right? The idea of the greedy is you're making an assignment, and you keep going, you keep going, keep going. So by the end, you have arrived at whatever the optimal approach is. And the metaphor that I used for this when I started taught it was I would talk about things like I would talk about puzzles. Again, imagine like a basic jigsaw puzzle. And right, the whole idea of a puzzle is you're not comparing every possible piece against every other piece in order to solve it, right? You just need to say, oh, this piece goes here. And once I've got that, it's like, then this piece goes here, then this piece goes here, then this piece goes here, right? You just need enough to get the next step in the solution, then the next step, the next step, the next step, and you build towards the solution. There's avoiding that kind of global thing. Now, we're going to talk about proofs, because I know we talked about proof by contradiction last week. We're going to talk about it again, but I'm going to talk a specific way of thinking about it, which is a sort of a what do you call it? A running proof? No, a falling behind proof. So we'll talk about this a little bit. Yeah, but generally speaking, so when you're looking for a greedy thing, this is the key thing, right? The solution must follow a consistent pattern that is easily determinable. And this pattern must be consistently applied at all intervals. And the solution will be optimal for all intervals. So at every step, it represents the most optimal solution up until that point. So let's sort of take this racing proof is what I want to talk about. So let's go back to our little problem here. What might be an organizing principle? Remember, you have cookies of varying sizes, and you have kids of varying amounts of greed. What might be an organizing principle for us to maximize the number of kids who are satisfied?
Well, you have to see how many first you have to see what the sizes of the cookies are. I would sort both lists first.
Okay, good. Yes, and there will be a sorting. Yes. So you do have to sort. Yes.
And then I'm actually thinking how to write the algorithm right now.
Before we even get in the weeds, think what's a basic, because right now I want a basic organizing principle. What's the rule? And this is purely logically. Don't think code, think logic for a moment.
Does the size of the next cookie does the size of the, iterate through the cookies, does the size of the current cookie satisfy the current child?
Yeah.
Okay, good. You're there. Yes. That's the basic thing. But so that's already, you're already talking like the algorithm,
Yeah.
which is good. But you got the basic. So let me take a step back, even behind you. The basic idea is satisfy the kid with the smallest possible cookie that will satisfy them. Right? That's the intuition. Because right? Because if you give them too much cookie, it's wasteful. Right? Because that's some kid who was greedier could have had that cookie and they could have done. So your intuition is exactly right. Give them the smallest cookie that's going to satisfy them. And that's where the sorting comes in. Right? So, okay. So the basic idea is you're going to sort your cookies in terms of size. You're going to sort your greed in terms of, again, lowest to highest. And then you're going to try to assign the cookies to the person as, right, the smallest possible cookie to the smallest greed. And you're just going to loop through it that way. All right. Now, before we write the code, before we get in the code. So, and again, right, it's not necessarily that hard to do this. I mean, this is just basically, just a, sort of some basic looping, right? It's the algorithm that's the trick. Let's talk about proof of correctness. How do we prove this? The intuition's there, right? I mean, logically, it seems sound. How do I prove that what I've done is correct?
That a higher number of kids could be satisfied.
Correct. So more generally, how do I prove that my algorithm will work? That my algorithm will return the optimal allocation of cookies such that, yeah, we've maximized the number of satisfied kids. So that's our, how do we prove that that's correct?
That the kids will be satisfied with a smaller cookie.
Well, more generally that my algorithm, so if my goal of my algorithm is to maximize the number of satisfied kids,
Yeah.
then how do I prove that my algorithm, the way we've talked about, which makes sense, right? Logically, what you're saying makes sense, but how do I prove it? How do I know that in the universe of possibilities, this algorithm is always going to return the optimal mix?
Wasn't it proof by contradiction?
Yes, proof by contradiction. So proof by contradiction says, right, assert that your algorithm fails, start from the basis the algorithm fails, and be detailed about why it fails, and then show why that isn't possible. And with greedy, there's a very specific way in which algorithms fail. And that's what we call a racing proof. So here's the idea. And sorry, I'm going to go, see, I'm going to go on screen here. Okay, I'm actually going to stop sharing for a moment. Let's see. Okay, I'm going to be on screen here so we can sort of see this. Because I think this is sort of helpful to visualize. So we have, right, so in our algorithm, we have, right, we have cookies and we have greedy kids.
Yeah.
And for every step of our algorithm, we are sort of, you can think about our algorithm kind of running. And every step of the way, we're allocating a cookie one to kid one, cookie two, cookie three, cookie four, right? We're allocating that. And right, because that's the greedy aspect of it. The greedy thing is, again, we're not making the global thing. We're not evaluating this cookie against every kid. We've just sorted and we've said, oh yeah, here, toss this cookie to this person.
Yeah.
Right? That's the greedy aspect of this. So a greedy proof says that every step along the way, we've made the most optimal decision up until that point. Right? Because we've always chosen the right thing up to that point so that we know by the time we've run to completion, it's optimal. Right? It's not like everything kind of falls into place after a while. Like it's not like it's doesn't work, and then suddenly it works. It's like every step along the way it's working. So that's what a greedy algorithm asserts. So for our algorithm to fail, right, proof by contradiction, we have to imagine that there is some secret hidden, let's start with secret hidden marker that works. I think if I get the angle, I'll figure this out. No, I just need a line with an arrow. I can. Okay, there's a line here somewhere. So imagine that there is some hypothetical algorithm that is better. And the key is, and when we teach this in class, we kind of get stuck on this because people start saying, well, what is this hypothetical algorithm? What is it? And the point is that it doesn't actually exist, right? This is imaginary because we're saying proof by contradiction says assume that my algorithm fails. And so if we say our algorithm fails, what does it mean for a greedy algorithm to fail? For a greedy algorithm to fail, there must be some other mythical algorithm out there that is somehow better, that's also running neck and neck with our algorithm, right? So we have our algorithm, O of n, running to completion, and then we have some other algorithm here running sort of at pace with us. And every step along the way, we're making the right choice. It's making the right choice. We're making the right choice. It's making the right choice. And somewhere along the line, our algorithm fails. We make the wrong choice, but this hypothetical algorithm makes the right choice. And our algorithm fails because of it, whereas this hypothetical one wins. Again, we're not saying anything about what this algorithm actually is. We're just saying hypothetically, if ours were to fail, that's what failure would look like.
And then when you say eraser, that means in the hypothetical of these greedy kids, it's a kid not getting a cookie for the other algorithm.
Exactly.
Okay.
That somehow we gave the wrong cookie to the wrong kid. Like we were doing good, we were giving the right cookie to the right kid, and then somewhere along the line we gave the wrong kid the wrong cookie. And everything just fell apart on us. Whereas we stumble, right? Imagine again, you're running, it's literally, we call it a racing proof because imagine visually, like you've got two runners, they're running, they're neck and neck, and then suddenly our algorithm trips, and then the optimal algorithm just zooms by. Right. So again, so that's the visual. And I think a lot of people get caught up in like, oh, but wait, what is this algorithm? Again, it doesn't exist. This does not exist. It's just it's a straw man we're putting up there.
Okay.
So from our perspective, right? So so again, proof by contradiction, we now have to say this is not possible. There's no way that our algorithm trips. So why is that the case? So again, our algorithm says we have sorted cookies, size, lowest to highest. We've kids, again, this doesn't work, lowest to highest. And then we loop through and we say, okay, here's the lowest kid. Does this cookie work? If the cookie works, assign, move on. If it doesn't, increment to the next cookie and try again. If it doesn't, increment to the next cookie, try again, until this kid is satisfied, then you move on. That's the algorithm. Okay? So, proof by contradiction. We've made the wrong assignment. To make the wrong assignment here, we know what's the failure, what's the inefficiency here? The inefficiency is we assign a cookie that's too large to a person, right? We over assign a cookie. This kid would have been fine with a cookie that's 5. We give him a cookie that's 10. There was a cookie out there that was 6, and there's another kid that's a 7. Again, if we had given the 6 to the 5 and the 10 to the 7, both could have gotten cookies. But because we gave the 10 to the 5, it doesn't work. Only one kid gets a cookie now. So our algorithm, so we're saying, well, because this always chooses the smallest possible cookie to give to the person, and the moment it finds the smallest acceptable cookie that's greater than or equal to size, we immediately assign and then we move on. There's no chance of us skipping the line, right? Because for this to have worked, we would have had to have tested that. It would be impossible unless we've allocated this to someone else, in which case, that's fine. Then we've already allocated someone else. But if this cookie is available, our algorithm will always check on this cookie first before moving on here, and we'll always allocate it.
And that's why the first thing to do is to sort of work the erase.
Exactly.
Oh, okay, that's where we're messing up. I didn't do this.
Yeah, so do the sorting. You absolutely have to do the sorting.
Yeah.
But so again, and again, that's where my suggestion when you're thinking about this is to work backwards from the proof comes into play. Because if you have this construct of thinking, okay, how does my thing fall behind? It's thinking defensively of like, what does failure look like? Well, failure in this case, again, says I should have, again, I'm sorry, like the thing again. What kind of, okay. So greed is 5 and 7, and a cookie is, okay, that's just making it worse. Quickly check if there's a marker hidden somewhere. No. Okay. Group. Greed is, yeah, okay. Whatever. Greed is 5 and 7. Cookies are 6 and 10. Again, if the 6 went to the 5 and the 10 went to the 7, we'd be good. If it flipped, we'd be bad. And so part of why our racing proof never works is we never make that misallocation, right? We never jump the queue and give the wrong cookie to the wrong kid. So again, that's where the idea of sort of working defensively, right? Thinking about, because again, it's this organizing principle, thinking about how, what does a suboptimal allocation look like? And then just build your algorithm backwards from there of saying, okay, well, how do I make sure I never make that wrong allocation? Okay, so again, so to recap, steps of our algorithm, generally speaking, right? We're going to sort both of them. And then we're going to loop through, and we're going to sort of loop through the overall program. And by the way, we're going to check to make sure that both we haven't run out of kids and we also haven't run out of cookies. That's going to be our overall while loop. And then we're going to say, okay, so now we're going to check and we're going to say, okay, and then we're going to look at particular, we're going to match a kid to a cookie. If the cookie is greater than or equal to the greed, assign, move both. If it's less than, move on to the next cookie. Try again. Move on to the next cookie, try again until it matches, then move on. Then move on, then move on until you run out of either cookies or kids. And then you return. You return the number. So, okay. I'm going to pause here. I'm going to give you guys a little bit of time to work through it. All right. I'm going to, hopefully you guys watching at home had a chance to test this out. Okay, so let me pull this up. Okay, so again, steps of the algorithm, right? So we start out by sorting both, right? Because we need pointers. So they both need to be ascended in sorting. Both need to be sorted in ascending order, which the basic sort algorithm will sort of do for us. There may be optimizations here, but I didn't sort of work on that. So we're going to do G sort and S sort. Right, so both of those are now sorted in ascending order. So I'm going to now initialize. So I used a while loop for my thing. Because I think that's a little better. Because while loops to me I find are easier to sort of increment on demand versus for loops. So I then both initialize. So I say I equals 0, J equals 0. Again, so we're doing like child I cookie J, right? So within these things, we're going to sort of initialize the pointers there. And then we're going to grab the length of sort of the tail end of both of these because we need halting conditions. So I'm going to grab both. I'm just going to call it N and M is equal to, and I'll do a sort of a dual assignment, length of G and length of S. Okay, so those are sort of my prerequisites. So what is my overall loop for this? So again, the overall loop is, while I both have not run out of cookies and I also have not run out of kids, right? Once either of those are run out, then nothing else to be done. So while I is less than, okay, so let me just make sure I'm doing this right. I guess I is less than. And I'll just have to, or yeah, and J is less than M. Okay, so that's going to be my overall loop again. Well, I still have cookies and I still have kids. So now I'm going to sort of reference, now I'm going to do my check. So remember the logic for our check here. The logic for our check is if the size of the cookie is greater than or equal, the size of the current cookie, right, in the array is greater than or equal to the kid's greed, assign that cookie and assign the cookie and move both forward, right? Move on to the next kid, move on to the next cookie. Else, if the cookie is too small, stay with the same kid, but move on to the next cookie, right? So that's the idea there. Okay, so I'm going to say here, so if S of J, so that's going to be like my little cookie. So if my current cookie, whatever my current cookie is in the array, is greater than or equal to G of I. So it's greater than or equal to the greed of the current kid. So if that's the case, then basically move both forward, right? So now I plus equals 1 and J plus equals 1. Okay? Else, right? So if it's not greater than or equal to, then again, move on to the next cookie. So move on to S. Sorry. Just move the size over. So J plus equals 1. Right. So again, so that's the basic mechanics of it. You have kid, you have cookie. If the cookie works, great, assign and move on for both. If not, move on to the next cookie, then it works, then move on, move on, move on. Until, and again, this loop will keep looping until you either run out of cookies or you run out of kids. Kids or cookies. Okay, now, which one do I return? So now I've finished my loop. What's my return here? And this is actually an optimization step because I was explicitly doing a count of it, but every time like this worked, I'd explicitly do a count. And then I realized I actually didn't need to do that. What I realized in the end is I just need to return cookies. And so, and the logic here is that if I write, so if I return kids, it could be the case where, because you're potentially, sorry. No, you return kids, not cookies. Sorry, it's the exact opposite. Correct. Exactly. It's how many kids you said. Because since you're incrementing cookies, you could, right? So the only way, because if you think about this, here, you're always going to move up. If you don't match, you're going to move cookies. So you can't return cookies because you could have a scenario where you match no kids against cookies. What would happen is this loop would loop all the way to the end. And you haven't matched anyone, it would still end. So you don't want to return cookies. So that was wrong. You need to return kids because the only way you increment on kids is when there's a match. So by definition, I is going to be the number of matches. So it's the number of satisfied kids. So return I. So yeah, so first I did a count and I was like, actually, I don't really need to do that. This should work. Okay, let me see if this is going to work. Run it. Okay, it's accepted. Let me submit. Okay. Okay. So my runtime, so good runtime. My runtime is 91 percentile. So it's a good thing. And my memory is not great. That's interesting to me. So only being 10%. So Kern, what were your?
No, I realized this. Instead of assigning the length, I what's it called? Assign the length of the list to variables. I kept having it recalculated every time.
Oh, okay.
Slowed it down.
Yeah.
So I removed that, assigned it. It did speed it up much more.
Ah, nice.
So I was getting down to the fastest I got was 11 milliseconds, 19.9 megabytes.
Oh, nice.
But that I'm averaging right now 22 to 23.
All right. So guys, any questions on this?
No, I see where I was messing up at because I was still working. I did the sort list, but I was going back to searching the first cookie.
Gotcha.
Yeah.
You weren't moving on from the cookies. Okay. Yeah.
I was following it, like I went through the whole list, like, oh, I couldn't find anything, so let me go back to the second move forward with the kid,
Yeah,
but then go back to the first.
gotcha.
Yeah,
Yep. And of
that's
course
what
that would, yeah. Okay.
Yeah.
Yeah. So again, this is an example, just kind of practice,
Yeah.
thinking it through.
But looking at this, in terms of redundancy,
Hmm.
couldn't we just do, remove the else? Remove the increment J under the if and just have it increment J always? So it would only increment I if the if statement was met, if condition was met.
Yes. Actually, yeah.
Would that add to efficiency?
Let's try that. So let's do that regardless. So the idea is you're always,
You're gonna increment J whether you're if or else.
I'm curious about that because yes, you're right. You're always incrementing. So let's do this. So yeah, you're right. So if that's the increment, that else just regardless do that. Let me just run this, see if this breaks anything. I'm curious as to what that does. Yeah, it still works. Okay, so we were at 15 milliseconds. Okay, look at that.
A little bit, yeah.
Yeah, so we didn't, so one less branching, one less variable update. Nice. Okay, yeah, look at that. All right, still didn't. I wonder what's going on with my memory. Why is this? I wonder if it's a sorting issue. Maybe the sort brings it all into.
But what, without sorting it, how else?
Yeah,
The logic would have worked though. Right?
I mean, I agree. I don't, let's see. I mean, well, there's not a huge distribution here, actually. If you're looking at this, the spread here. So yes, technically, oh wait. So my memory is actually good. Why? But I mean, the point is you can see here, it's not a huge distribution. So 19.7 versus 19.8 versus 20. You're really looking at sort of a marginal thing here. And actually for runtime, I'm sort of curious. So here, some people are up here. You got some folks getting way down here. But yeah, it's kind of cool, right? So it is worth kind of looking not just at the raw number, but looking at the distribution. Because sometimes it just might be pointers and whatnot. Okay. Any other questions on this problem?
No.
All right. Well, all right. On that note, I will stop there again. I think this is another sort of example here where, the trick, right? The code itself, relatively straightforward. Nothing sort of what I'd consider advanced Python. It's really just sort of thinking through the algorithm.
Yeah. It was more of like trying to get away from going back to like the original. 'Cause
Yeah.
I'm still trying to do like.
Yeah.
brute force.
It's a brute force. And that's fine. And that's like I said, with this, it's always when you're looking at these things, it's always easy after the fact to be like, oh yeah, of course this was greedy. It's not always going to be greedy. And it's perfectly fine to start with a brute force for it. So it's, particularly for these things, like if you're given an hour, it's perfectly fine to be like, let me do a brute force, get it working, pass all my tests, and then see if there's sort of an algorithmic optimization. Like you still want to take that approach because you don't want to, at the end of the day, they're going to look at they're going to look at, did you, we gave you an hour. Did you pass these tests?
And I guess like for our own like practice, like at home or whenever.
Yeah.
Let's say we do like a a solution. So for example, if we would have done additional, nested loops,
Mhm.
we would have got O of n squared.
Correct.
Would you recommend like going to AI, like asking AI,
Yes.
okay, oh, okay, this is.
That is, I mean, to be perfectly transparent, that's my approach.
Okay.
That's 100% what I do. I work the problem myself. I try to understand the problem, try to get it working, try to think about things. And then 100% I go to ChatGPT after it's like, hey, how would you do this? And invariably they do better. So what I'm presenting to you is not,
Yeah.
this has been very heavily assisted by other things. So yeah, that's exactly the approach I would take. And then you could be like, oh, that's how I could do it. And then you go back and you sort of redo it that way.
And then there was another question like that,
Mhm.
it's more of like, it's like more related to like data structure and algorithms.
Yeah.
If. It's kind of like, I guess it kind of compared to like bootstrap, like, let's say if we had to do like a leak list or
Mhm.
like a. make like an algorithm that like divide and conquer.
Yeah.
Is it possible to like look at someone's like highly optimized algorithm and copy and paste that? I guess to kind of to make it seem like, let's say I'm drawing a picture of a tree, and hopefully this analogy makes sense. I know that I won't be able to draw the best tree, you know, because maybe I don't have like the math to like, you know, find the most optimized algorithm, but
Right.
I know what I'm looking for. Is it possible to get like a really good algorithm and just try to like, make it fit into your program, or it won't work? It'll be more hardy.
I think it would be harder to try to force like something like greedy is a paradigm, and it's easy enough to sort of drop it and be like, oh, this is greedy, here's how this applies, versus say taking like pseudocode or code and trying to like swap out variables. Because like even within greedy, there's so many different versions and permutations and things. You'll spend more time thinking through and correcting and modifying the language, I think, than just kind of doing it yourself. Because I mean, look at, imagine if like you took the greed, like last week's was a greedy algorithm.
Yeah.
This week's is a greedy algorithm. But like, imagine how challenging it would be to take last week's code, plug it in here, and then try to like force the logic into alignment with the particulars of this.
Yeah.
So I think that instinct is there, and that's one of the things. Like when we train on LeetCode, like one of the things you think about is you start saying like, does this example look like greedy? Like, and this is even left like we did for LeetCode, but also for like exams. Like when we were, like when we'd be prepping for algorithm exam, like we'd give people these algorithms, and be like, how do you solve them? And one of the things you try to do is you try to be like, try to fit it into a box. You say, is this greedy? Is this dynamic programming? Is this divide and conquer? Is this, interval scheduling? Is this something like some other sort of paradigm for this that we can sort of structure? So you do think in terms of paradigms, but you don't think at the level of let me copy and paste code and then swap out variables. I think it's not quite that modular.
Oh, okay. So like for example, like let's say we know that like a greedy approach is like open.
Mhm.
That doesn't necessarily mean that I could go on to Google or ChatGPT and search up, best greedy algorithm and then use that.
Correct.
Yeah.
Yeah, because greedy is more a way of thinking about it. It's a way of structuring and thinking about algorithm than an actual code is a way of thinking about it.
Oh,
It's not like a library, like import from Python, import greedy.
yeah.
Yeah, it's not at that level
So
of
not like bootstrap.
Exactly.
Like a radio button and just
Exactly.
Okay.
And I looked at the code submissions for the guys who had like the 0 millisecond ones. It's like the exact same algorithm.
Oh, really?
Yeah,
Oh.
they just got lucky. So the one thing that they did do was they added a third variable or a fifth variable for count.
Oh, well, that's what I did originally.
No.
Okay. Oh, okay.
Original?
I had, yeah, and then I realized that it was just
redundant. Yeah.
child. Yeah, so I got rid of it.
Yeah.
I thought that was an
but
optimization.
all the ones that have the fastest time.
Yeah.
All have a count.
Fascinating. But
So
why?
I think that would be slower because
Yeah.
it's taking up more memory.
Yeah, and you have to do there's an added step because every time you increment, you have to.
More memory.
Yeah. Okay, that doesn't. Yeah, I mean, it just shows you at some point this is all just.
Could it be that they
Flukes.
have like
Well, you're running on LeetCode's cloud, so
So it just so happens they might have submitted when their cloud was like empty.
right, exactly. So there was no.
Their
Yeah,
cache
exactly.
cleared out.
Yeah. Yeah. So I think, we shouldn't read these numbers too. I mean, right, if you're like 10% and there's a huge distribution, then maybe, yeah, but yeah, at some point there's a luck of the draw here. You're looking at cache, we're looking at available memory, things like that can all impact runtime. All right, cool. I'm gonna end the recording there.